Thanks for the introduction. Today, I would like to introduce my research about visualization design and evaluation on different displays. First of all, what is visualization? Nowadays, huge amount of data has been collected. The raw data usually look like this. Visualizations are tools to translate this raw and complex data into meaningful graphics. But why are we doing this? Could we just use the raw data? The strongest motivation is for productivity. Let us see a quick example. Here are a bunch of numbers. Can you identify the top 5 numbers in this table? This probably will take you a while. Let us then use color to encode the numbers. Now you can probably find the top 5 instantly. This is because for the raw data, human brains can only process one number at a time, while for visual graphics, the processing is happening in parallel, which of course is much faster. In addition to the previous simple examples, visualizations have been also widely used in data analysis and information communication. Generally, visualizations leverage perception to summarize data in a cognitively efficient way, making them popular in science, analysis, and the media. Various visualizations exist. However, existing visualizations may not work in some scenarios. For example, the media frequently use carpet maps to communicate the election results. With a carpet map, such information can be misleading. Like here, red is predominant in the map. However, blue has more electoral votes. We need a more effective visualization to communicate election results. The New York Times has created a new way to better visualize such data. They use one small square to represent one electoral vote, and then carefully place the squares to represent the votes for each state. It is showing the number of votes accurately and keeping the shapes and locations of different states legible. This is a great example of novel and effective visualization. However, coming up with novel and effective visualization design is not a trivial task. So how to design effective visualizations, and how could we know a specific design is effective? This is the main topic of today, visualization design and evaluation. Tamara Manzner is one of the most influential researchers in the visualization research community. Her book, Visualization Analysis and Design, is one of the most widely used visualization textbooks. In her book, she pointed out 3 most important things we should consider in visualization design: computers, humans, and displays. Let us quickly go through them. Visualizations exist far before the computer has been invented. Without a computer, creating a visualization is a time-consuming task. For example, drawing the presented visualization may take a few weeks or even months. Most visualizations now rely on computational power to calculate parameters for visual elements, like the position, shape, size, and thickness. As a result, producing a similar visualization may only take less than a second. Furthermore, in many applications, the calculation power also enables interactive exploration. Encoding numeric values into visual elements is one of the most important steps for visualization design. Many visual channels can be used to encode data values, like angle, height, area, and color. Humans perceive those visual channels differently, resulting different effectiveness from them. Like here, these 4 visualizations are showing the same data, but only from the bar chart you can really tell the difference between A and D. Past research has figured out the effectiveness among different channels. However, this chart only provides guidelines for the most basic situations. For more complicated scenarios, this guideline may not work anymore. More research is required to understand the human factors in those complicated scenarios. Displays are the media for visualizations. We are all familiar with flat 2D monitors. Before that, visualizations have been created with papers and pens for hundreds of years. We can still see many printed materials in our daily life. With popularity of mobile devices, we can now easily access information without a computer. Immersive technology has been rapidly developed in the recent years and bring high-quality VR, AR head-mounted displays to normal people. We can even create physical visualizations using techniques like 3D printing. Different display technologies provide different capabilities for data visualization in terms of how the data can be visually represented and how people can interact with those visual representations. With these three types of resources, how can we systematically approach novel and effective visualizations? My strategy is starting from existing techniques, systematically analyze the pros and cons, and then carefully consider these three types of resources and build novel visualization and interaction techniques. Finally, I run user studies to provide empirical evidence for the newly created techniques. One unique aspect of my research is that I'm particularly interested in the displays. I believe leveraging the capabilities of different displays can better support specific scenarios. Therefore, using the mentioned research methodology, I have developed and evaluated novel techniques on flat screens, in VR, AR, and in physics format. I will introduce selected projects from each category today. I'll start with Matrix, a novel visualization we created on the flat screen. On the first day of my PhD, my supervisor Tim asked me, "What do you want to do for your PhD?" I saw Tim is an expert in network visualization. I was obsessed with maps at that time. Why not adding them together? So I decided to do research about visualizing geospatial network data. A geospatial network represents movements between different locations. Such data may include migrations from one place to another, movements of commodities, or even abstract things like knowledge and disease. It is important for analysts like urban planners, healthcare researchers, migration officers to effectively understand the data to better support their decision-making. For example, visualizing tracing of COVID-19 cases can help people better understand the spread of the virus and help governments establish effective policies. However, visualizing geospatial network is a challenging problem. The most popular visualization method is drawing arrows on top of a map. This is easy to understand, but overlaps introduce visual clutter for large data. Another way is to use a matrix to represent the same information. It is much more scalable. However, the matrix alone does not provide any geospatial context. So can we have the benefit of both in just one visualization? We studied our first design. In a matrix, rows are for origins and columns are for destinations. I put a map at the left side to match the rows and another map at the bottom to match the columns. A single flow comes from the origin in the left map and linked to its row in the matrix and goes to the destination through its columns. In the same way, we can connect all the origins to the rows and all the destinations to the columns. This is our first attempt to combine these two visualizations together. As you may notice, the line crossings affect the legibility of the visualization. We found a promising technique to solve this problem, which is called boundary labeling. However, their techniques have a few limitations which cause confusions in some situations. For example, a line may come across a point, or two lines totally overlap, which create ambiguous representations. When lines are too close to each other, it is also very difficult to track. To solve those new problems, we invented our quadratic optimization model to improve the boundary labeling. Basically, after getting the initial results from the boundary labeling, we slightly move the points to solve the problem. First of all, we want to minimize the moving distance. We then make sure the node is still within a bounding box. And finally, we push away lines that are too close to each other with a minimum distance. Now, we can produce really nice connections between maps and matrix. It is also possible to present flows from one country to another different country. However, rows and columns are in different orders, making it difficult for people to find the information they want. To address this issue, we move both two maps to the left side and rotate the matrix. This is the final design of matrix. We were super happy about our design. An important next step is to understand how effective matrix is. To achieve this, we compared it with two state-of-the-art techniques. The 9 flow maps connects origins and destinations with straight lines. However, the overlaps makes the visualization illegible. Bundle the flow map routes the arrows to make the visualization easier to read, and it is the first technique we compared with. Another technique is called OD map, which first create a grid map for a geographic map. This single grid map can represent one to many flows. In this case, we are showing flows from NTL to other states in New Zealand. Then duplicating the grid map for other locations can represent many-to-many geospatial networks. Another important step for evaluation is identifying the study tasks. To achieve this, I interviewed domain experts who are dealing with this type of data in their daily workflow. I then analyze interviews and identify 6 abstract visualization tasks from them. I'll use Matrix to demonstrate these tasks. The first task is comparing 2 single flows. We can find the first origin and its row, and the first destination and its column. Then the intersection is the value for the first flow. We then use the same method to find the value for the second flow. And now we can compare these 2 colors. The second task is finding the largest flow. We first find the darkest cell in the matrix, and then find out the linked origin and the destination. The third task is find the largest flow to a given location. We first find the origin and its linked row. From this row, the darkest one is the flow we want. We then find its linked destination. We also look at total flows that are associated with locations. The first total flow task is comparing 2 locations. We can find the first location. Its circle or the bar chart stand for its total flow. In the same way, we can find the other location and compare them. The second total flow task is finding the largest total flow. The participant can search the largest circle or the police bar chart and find its linked location. The last type of task is for regional flows. We define region as a set of locations. The regional flow task is compared the aggregated flows of 2 regions. In this example, we can find the first region and the flow within it. In the same way, we can find the second region and flow within it. Now we can compare the aggregated values. We then compare the different visualization techniques in these different tasks in 2 user studies. We recruited participants from research institutions and visualization mail lists. After collecting the data, we used the R to build statistical models to analyze the significance of the comparisons. Here, I want to just provide some high-level results. Basically, we found all methods perform well on small data. Matrix and OD map perform much better than the bundled flow map on large data. And there is little difference between Matrix and OD map, but people like the Matrix more. Based on the feedback from our participants, we also design interactions to better support analytic tasks like highlighting and selection. Filtering the flows by value and allow the user to group regions. In this project, we have designed and evaluated the novel visualization for geospatial network data. Matrix is capable of presenting large data while still showing the geographic context. With Matrix, data analysts can find the desired information effectively and potentially identify unexpected and important patterns. Because of its novelty and effective design, Matrix has been featured by many visualization practitioners and researchers. It also received an honorable mention award at IEEE's conference. In addition to geospatial network data, I've also used the same methodology to design and evaluate visualizations for hierarchical data and use the physiological measures like EEG to better understand cognitive load in visualization use. Due to the time constraint, I would like to move on to my next major research direction. the immersive visualizations. With VR/AR, I have built novel geographic visualizations, embodied interaction for navigation, and real-world applications. Before diving into specific projects, I would like to bring up a fundamental question. Why are we starting to pay attention to VR/AR now? Immersive display is not a new idea, but back to 1968 when the first VR head-mounted display was built, the device was bulky and expensive. People were passionate about this revolutionary technology and keep investing in it. Because of this, we can now have a lightweight and high-quality head-mounted display at a reasonable price. With the mature hardware, it is timely to explore what VR/AR can bring to visualization and user interface. Based on my experience, I identified three most notable features from VR/AR that flat screens cannot offer. The first one is 3D rendering. 3D rendering is a natural choice for 3D data with intrinsic spatial layout. For example, some geospatial data, scientific simulation, and medical data. In one of my previous projects, we compared globes and maps for presenting world geography in VR and found advantages of using globes. Additionally, 3D rendering provides more space to reduce visual clutter. For example, in a previous project, we lifted the arrows from a flat map to the third dimension and found people could find the information more effectively with the 3D version. 3D rendering also allows the use of the third dimension to encode data values. I'll demonstrate this in a project with more details later. In summary, my past projects demonstrate the possibility of using the third dimension to build more effective visualization in VR and AR. Secondly, VR/AR also offers a large display space. With the infinite display, we can remove the boundaries of physical displays and create new human-computer interaction experiences. First, we can create an unlimited number of displays at any position in the space, just like demonstrated in the figure. Furthermore, we can create novel visualizations. For example, I have developed a novel way to present world geography, which places the user inside a very large globe, like a hamster. Finally, VR/AR allows us to interact with graphics with embodied movements. The user can grab and move virtual objects in VR/AR, as well as moving himself. As a result, the user can easily find a good viewpoint for the desired information, just like demonstrated in the video. Furthermore, embodied movements allows us to build novel interactions. For example, this video demonstrates a visualization ordering system from my previous colleagues at Monash University. In their system, the user can grab data axes to build various visualizations, like scatter plot and parallel coordinates. The user can also grab a new data axis and attach to an existing 2D visualization to create a 3D visualization. Here, you see a 2D scatter plot becomes a 3D scatter plot. One of my major research interests here is to explore how to leverage these features to build more effective interactive visualizations. Here, I would like to introduce two of my recent projects. I'll start with the tilt map, a novel embodied interaction technique we built in VR/AR. Cartpath maps have been widely used to present data associated with geographic locations. For example, unemployment rate, birth rate, population density, and many more. Various people and organizations are using Cartpath maps to reveal patterns in their data and support their decision-making. The basic idea of Cartpath map is using colors to encode numbers from small to large. You may still remember, as we discussed at the very beginning of this talk, there are other ways to encode numeric values. Some encodings are more effective than others. We can see color is not a very effective encoding. The most effective encoding is actually height. As Cartpath map is created by using color to encode values, we can also encode the value with height and we will get a prism map. It is hard to tell it is 3D from a vertical view. Let me rotate it to demonstrate the prism map from different angles. Cartpath map is familiar to people. However, it uses an ineffective encoding. Prism map uses an effective encoding. However, occlusion is inevitable in this representation, especially when seen from the side. It is also possible to use both color and height to encode the data. The idea of using height to create prism maps is not new. People started to use them more than 40 years ago. Now there are many software supporting the creation of prism maps. They have been also widely used by visualization practitioners and data journalists to tell data stories. However, are these prism maps really effective? We found a few, but very limited number of evaluations. Limited benefits have been found with prism maps. This is expected, as these studies were conducted on 2D flat screen and without any interaction. As a result, the participant could only see the visualizations from one fixed viewing direction and suffer from occlusion and perspective distortion. We believe 3D visualization works much better when the user can easily and intuitively change their view position and direction. In VR/AR, the embodied interaction allows the user to manipulate the visualization by grabbing and moving it. The user can also move around the visualization to find the optimal viewpoint. With embodied interaction, the issues of occlusion and perspective distortion from 3D rendering can be alleviated. To prove our hypothesis, we conducted a user study to evaluate these three different visualizations. We tested the visualizations with two tasks. The first task is an elementary task. Basically, we ask our participants to compare two values. But instead of just identify the larger one, we ask them to estimate the difference between the two. We expect this can give us a more nuanced understanding of the performance. We also tested another summary level task. We asked our participants to estimate the population density of a few contiguous areas. This is basically the weighted average of a few regions. Let us have a look at the high-level results. Overall, we found corpus maps were fast but less accurate. Prism maps were slower but more accurate, and participants clearly prefer colored prism maps. As each view has its own advantages and disadvantages, we started to think how we can have the benefits of each. During the user study, I observed that participants tilted the visualizations into different angles to use them. This makes sense. We can see corpus map and prism maps look very similar when they are just vertical. However, they look very different when the user tilts the map. If the user wants to use the height in the prism map, they have to tilt the map to see from the side. I then systematically analyzed the collected interaction data. The data confirmed my observation. Our participants place corpus map vertically most of the time, while they frequently tilt the prism map to see from the side. Look, one important thing here is there is no overlap in the use of tilt angles. So why not let the tilt angle determine the view? That is, when the view is vertical, we show a prism map to the user. And when the user tilts the view to a horizontal angle, we change it to a prism map. However, when the prism map is perfectly horizontal, the occlusion prohibits the user to find the information effectively. Like the prism map, another widely used visualization that uses height to encode data values is the bar chart. We decided to present the bar chart when the view is perfectly horizontal. These are the three main views in our system. As the tilt angle is continuous, we designed intermediate views to support smooth morphing between the three different main views. Taking advantage of embodied interaction in VR/AR, the user only needs small wrist movements to seamlessly switch between the three main views. Let us see this in action. The user will first see a corpus map, and then as he tilts the map, it morphs to the prism map. With continuous tilting, it morphs to a bar chart. We call this interactive technique tilt map. Let's see it again. So first corpus map, prism map, you have bars on the map, and finally the bar chart. Another way to have the three main views together is placing them side by side. Here, the user needs to rotate his body or head to switch between views, and it does not have the intermediate views. Alternatively, the user can toggle between views. Basically, the user clicks on a button to switch the view. It provides an interaction which is very similar to the desktop environment. We conducted a user study to compare these three interactions. In summary, we found our tilt map was more accurate than side-by-side and faster than the toggle. In this project, we introduced a novel interactive visualization technique in immersive environment. Tilt map provide an embodied way to switch between views with different advantages. With tilt map, the analysts can easily switch between views to explore data more effectively. In addition to the technical contribution and the empirical evidence, this project also demonstrates how we can take advantage of 3D rendering and embodied interaction in VR/AR to build effective visualizations. We have one thing left, the large display space. Display space is always an important real estate for visualization. As discussed previously, in VR/AR, we can have a much larger display space compared to desktop monitors. However, large size alone does not necessarily mean more effective. We need to support the user to effectively find the required information in the large space. Here, I would like to introduce how we designed and evaluated navigation techniques for data visualizations in VR and AR. Let us first look at how people navigate on 2D screens. The display space is always limited on a 2D screen and only can show part of the information. Sometimes you need to go to specific targets outside of the screen, just like the marked one. Panning is a basic navigation method which allows you to go to different places. However, without knowing where to go, panning alone is not effective. Additional interactive support is essential. Zooming scales the view up and down. The user can first zoom out to an overview to identify the location of the target, and then zoom in to look at the detail. Another option is using overview plus detail technique. In an overview plus detail, we use a small window to show the full information space and use the rest of the display to show the detail view. As we can easily access the full information space in the overview, we can easily figure out which direction we should move. However, these methods only apply to 2D screens. How about we enlarge the display space like a dozen times and even with one more dimension? What interactive support should we provide? This is a problem we explored in this project. One obvious direction is looking at these two well-established navigation methods and figure out how to adapt them into the 3D large display space. For zoom, we choose to adapt the pinch-to-zoom mechanism. Two controllers can act as multi-touch inputs. However, we found a new challenge. The knife pinch-to-zoom method only considers the scale of the object, but during the zoom, the user may also move and rotate the object. Only change the scale may even move the object away from the controllers, which obviously affect the user experience. To tackle this issue, we implemented a latched pinch-to-zoom mechanism, which allows the controllers to stay at the same relative position to the object. The basic concept of overview plus detail is simple, but there are many other design decisions for immersive overview. For example, where to place the overview. On a 2D screen, the overview is usually placed at a fixed location, for example, at the bottom right corner. Following this idea, we attach the overview to the bottom right corner of the field view and allow the user to pick it up. We piloted this idea with two participants. Both participants found the overview distracting and cluttered. We came up with another idea. We attach the overview to a controller so the user can easily hide and access it with simple arm movements. We also shrink the size of the overview by default and allow the user to enlarge it by simply putting the other controller inside. The user can also grab the overview, move or rotate it. When creating overview for a 2D visualization, it is important to indicate the region of the detail view in the overview. Following the same idea, we created an object showing the real-time position and orientation of the user. This is useful for many scenarios. For example, here, the user notices the yellow target is on the left to the indicator, then he can simply turn left to find the target in the detail view. We also allow the user to use the overview to teleport. Let us first introduce the drag and drop teleportation. The user can pick up the indicator and move to a new position, and then release to teleport. We also provide another way to teleport, point and click. The user only needs to move the controller to the target they want to see, and then click to teleport. We designed and conducted a controlled user study to understand the effectiveness of these different navigation methods. We consider the zooming and overview techniques as 2 dimensions and systematically compare them in a complete matrix. Here, I will demonstrate the key findings from the user study. We found adding an overview is beneficial for the baseline condition, but unnecessary for the zooming condition. Overview plus detail was more accurate than zooming in some tasks, but zooming tended to be faster. We also found the baseline condition was faster than zooming condition in some tasks, which means body movements is more effective than object manipulation. We can see there is no clear winner. We also found the baseline condition performed generally well, especially in terms of time. This is unexpected because without interaction support, participants should need more time to navigate in the space. This is also reflected by the feedback and the interaction data. Participants complained frequently about the difficulty of finding the targets in the baseline condition. We want to figure out what happened. We found out navigation is a complex process with multiple components. We identified 4 components from the literature. Wayfinding is the process of finding the destination. Travel is the modal part to get to the destination. Number of travels can also be different in different conditions for completing certain tasks. Context switching is when the perceived view changes. The user needs to reinterpret the new environment based on expectation. We then analyze the performance of our tested conditions in each component. For wayfinding, we believe overview plus detail has the best performance, as the user can use overview to find the target. Zooming with overview also provides overview, but participants found overview disturbing. In a zooming interface, the user can only access the overview when zoomed out. In the baseline condition, the user does not have any support for wayfinding. We use our collected interaction data and the user's comments to analyze travel and number of travels components. Due to the time constraint here, I directly represent the results of these 2 components. For the context switching cost, when using an overview, the user needs to map the information from the overview to the detail view, or use teleportation to suddenly jump to a new place. We believe these operations have the highest context switching cost. In the baseline condition, the user has a spatial continuous experience. However, participants also performed a significant amount of teleportation, which introduced some context switching cost. On the other hand, the zooming interface has the best performance. In this project, we adapted 2 well-established navigation techniques from 2D to immersive environments. With our techniques, the user can better utilize large display space in VR and AR. Our navigation time cost model also provides radical guidance for both technical design and task analysis. With these guidelines, visualization designers can further improve the navigation techniques in VR and AR. In the last project, I'm going to demonstrate our attempts to make visualizations more accessible with physical representations. Visualizations have been widely used to present data. Taking advantage of the powerful human visual system, visualization is a highly productive way to communicate information. However, this is only for sighted people. For blind or low vision or BLV people, they cannot benefit from visualizations directly. Furthermore, due to the popularity of visualizations, many important information becomes inaccessible to them, like many COVID-19 graphs. In this project, we created accessible network visualization for blind or low vision people. We used a special material to create tactile graphics, which is called swirl paper. It basically swirls along black lines after being heated, so the blind or low vision people can actually touch the graphics. We choose network data for this project as it is widely used and has not been studied before. We investigate this by first exploring the design options and then conducting a user study with experienced touch reader on swirl papers. Node link diagram are the most widely used way to visualize network data to sighted people. But for blind or low vision people, the most familiar representation actually is in the format of text. In the text representation, we simply describe the neighbors of each node. For example, here, A is friends with C and D. We do the same for all nodes, and then use Braille to create tactile representations. Apart from node link diagram, an alternative graphic representation is a matrix. In a matrix, each row or column is showing one node. We use a circle as an intersection to indicate there exists a link between two nodes. Here, we are showing the link between A and C. Keep repeating the process, we will have the matrix showing the same information in a node link diagram. An important design choice for node link diagram is the layout. Force direct layout is the most widely used layout for node link diagrams. Alternative to the force direct layout, placing nodes on regular grids has been tested to be preferred by sighted reader. Such an orthogonal layout is likely to reduce memory load, and the blind or low vision people might find it easier to build an accurate mental model of the network. We conducted a user study with 8 experienced touch reader on network analysis tasks with different sizes of networks. In summary, we found node link diagrams are the overall winner. They were faster and easier for the tested tasks. There is also little difference between the two different layouts of the node link diagrams. Participants performed unexpectedly badly with the matrix. Participants found it by far the hardest representation to understand. One particular difficulty was understanding that the matrix was symmetric and that the diagonal was a line of symmetry. Such information is apparent visually, but not when explored by touch. Surprisingly, we found text representation performed reasonably well. However, participants' comments revealed that it placed a higher demand on working memory. It thus may have difficulty scaling to large networks. This research contributes to a more nuanced understanding of how to build visualizations in physical format for BLV people. These are the projects I would like to demonstrate today. In my future research, I would like to build interactive visualizations on different displays and in different forms. I'm excited about the different capabilities of these different platforms and would love to utilize them to increase productivity. I would like to have a particular focus on immersive displays. This is because I believe VR/AR will be an important component in the future workspace. It allows us to remove the boundaries of physical screens and provide opportunities to fundamentally change how people work. It can eventually display 2D monitors in many scenarios, as you can always create unlimited 2D screens in VR/AR, just like demonstrated in the right figure. Furthermore, VR/AR offers features that 2D monitors are not capable of. With VR/AR, one can create 2D and 3D visualizations, place them at any position in the infinite screen space, and use embodied movements to interact with them. With these features, I believe VR/AR can further push the productivity of data analysis and communication to the next level. Delivering on this promise requires deep integration between hardware, software, and user experience. After years of development, the required display and interaction hardware technologies exist today. However, the fundamental human-computer interaction research needed to realize these scenarios is simply not there. I would like to devote myself to investigating how to fully harness this new and amazing technique for productivity. More specifically, I have been involved in a working group focusing on identifying the grand challenges in immersive analytics. Our recent paper has been accepted at CHI 2021. Within the many research directions discussed in the working group, I'm particularly interested in the following three areas. I would like to design and conduct user study to understand different aspects of human factors and user results as guidelines to design immersive applications. I also want to build a collaborative visualization system to support different types of collaboration scenarios. AR has a huge potential for data analytics as it allows the user to see both the physical and the digital world at the same time. It can bring data out of the computer and into the world around us. I want to leverage this feature to enhance existing working flows. In addition to the previously mentioned fundamental HCI problems, I also would like to work with domain experts to build real-world applications. AR provide easy to access and intuitive user interface for IoT, while IoT can be data sources for situated analytics. VR AR can also be used in manufacturing, medical, and sports applications. For instance, VR can be used to provide immersive training. This is especially useful to simulate scenarios that are too expensive. Like I know NASA is currently using VR to train their astronauts. AR can support workflows with situated guidance and hands-free access to visual information. To this end, I would like to quickly mention one of my most recent projects to demonstrate a small portion of the possibilities. Together with a PhD student I supervise at Harvard, we have built an AR visualization system to support basketball free throw training. This work has been accepted at CHI 2021 and received the Honorable Mention Award. To conclude my talk, I would like to thank my supervisors, students, and collaborators from all over the world. Here are some of their smiling faces. I would like to stay on this slide for a little bit longer, if you don't mind. Thank you very much for your attention. I would like to take any questions if there are any. And you can also reach me through email. I'm happy to answer any questions you have. Thank you very much.